Somewhere in the last 6 months, a team of astronomers pointed the most powerful telescope humanity has ever built at a planet 124 light-years away. And for a few weeks, a large part of the scientific world genuinely wondered if we had just found the first hard evidence of life beyond Earth. That planet is called K2-18b, and the molecule at the center of the controversy is dimethyl sulfide, a gas that, on our own planet, is produced almost exclusively by marine organisms like phytoplankton. No volcano makes it. No lightning storm makes it. As far as we know, on Earth, only life makes it in meaningful quantities. So when the James Webb Space Telescope picked up a possible signature of that same gas in the atmosphere of a distant sub-Neptune, headlines exploded, and the public conversation jumped straight to little green men and flying saucers. The real story is far stranger, far more careful, and far more interesting than that, and it says something important about what alien life would actually look like if we ever found it, and how differently that discovery would unfold compared to what science fiction has trained us to expect. Let's start with the planet itself, because K2-18b is nothing like Earth, and that matters enormously for what kind of life, if any, could exist there. It's roughly 8.5 times the mass of Earth, and about 2.5 times the radius, which puts it in a category we don't have an example of in our own solar system, somewhere between a rocky world and a gas giant. Astronomers call planets like this sub-Neptunes, and one leading hypothesis is that K2-18b could be what's known as a Hycean world, a planet with a deep liquid water ocean sitting underneath a thick hydrogen-rich atmosphere. If that picture is correct, it would be a completely different kind of habitable environment than anything we have direct experience with. A permanently dark, high-pressure ocean world with no surface in the way we'd recognize it, sealed beneath a blanket of hydrogen gas. In 2023, Webb detected methane and carbon dioxide in that hydrogen-dominated atmosphere, and researchers noted that this particular chemical mix was difficult to explain through standard atmospheric chemistry alone, which is part of why the Hycean hypothesis gained traction in the first place. Then came the harder claim, a low-confidence hint of dimethyl sulfide in that same 2023 dataset, followed by a more detailed mid-infrared observation in 2025 that reported a stronger, though still far from conclusive, signal at roughly 3 sigma confidence for dimethyl sulfide, and a related compound called dimethyl disulfide. 3 sigma sounds impressive if you're not familiar with how statistics work in physics and astronomy, but it isn't the gold standard those fields actually require. In particle physics, the threshold for calling something a genuine discovery is 5 sigma, a level of statistical certainty so high that the odds of the result being a random fluke are less than 1 in a few million. 3 sigma results, by contrast, have a history of falling apart on closer inspection. It happened with the phosphine detection on Venus back in 2020, a finding that was initially reported as a possible biosignature and treated by parts of the media as strong evidence of atmospheric life, before follow-up analysis found more mundane explanations for the same data. The scientific community learned a hard lesson from that episode, and it's one of the reasons the response to the K2-18b DMS claim was so much more cautious the second time around. Multiple independent teams went back through the Webb data. Some reanalyses using the full suite of near-infrared and mid-infrared observations together found no statistically significant evidence for dimethyl sulfide or dimethyl disulfide at all once the datasets were combined. Other groups pointed out that the original 3 sigma claim was sensitive to exactly how the atmospheric retrieval models were constructed, meaning a different set of reasonable assumptions could shrink or erase the signal entirely. As of the most recent published reanalyses, the honest scientific consensus is that the case for life on K2-18b does not currently meet the standard of evidence required to call it a biosignature, and researchers have explicitly said so in peer-reviewed work, describing the detection as failing the key statistical and interpretive criteria that any legitimate biosignature claim needs to clear. This matters for your understanding of the bigger picture, because it tells you something crucial about how the actual discovery of alien life is going to happen, if it happens at all. It will not arrive as a single dramatic press conference with a clear yes or no answer. It will arrive the way K2-18b has unfolded, as a slow, argumentative, statistically messy process, with claims made, claims challenged, data reanalyzed, and confidence levels debated for years at a time. Real astrobiology does not look like the third act of a summer blockbuster. It looks like committee meetings and competing arcs of papers. And that painstaking process exists precisely because scientists have been burned before by jumping to conclusions, and because the stakes of getting it wrong or right are almost too large to comprehend. So if the discovery process is going to be this careful and this slow, what should we actually expect the life itself to look like, assuming we eventually find real evidence of it? This is where the conversation gets genuinely fascinating, because researchers across astrobiology, biochemistry, and planetary science have spent decades working through this question, And their answer is almost uniformly the opposite of what popular culture has taught us to imagine. Forget humanoid aliens with slightly different foreheads. Forget articulate reptilian overlords or elegant floating orbs of pure energy. The overwhelming scientific expectation is that if we find alien life, especially the first alien life we ever confirm, it will be small, simple, and almost certainly microbial. There's a very grounded reason for this expectation, and it comes directly from looking at our own planet's history. Life first appeared on Earth roughly 8 billion years ago, and for well over 3 billion of those years, every single organism on the planet was single-celled. Multicellular life, the kind that eventually produces something with eyes, limbs, or a nervous system, is a relatively late and comparatively rare development in the story of life on Earth. Complex macroscopic organisms are the exception, not the rule, even in the one place in the universe we know for certain hosts, life. If that same pattern holds elsewhere, and there's no strong reason to think it wouldn't, then any given inhabited planet is statistically far more likely to be caught in its microbial phase than to have already produced something we'd recognize as an animal, let alone an intelligent civilization capable of building spacecraft or broadcasting signals. Scientists studying this question have pointed out that alien life is more likely to exist on a scale we can barely appreciate with our own senses, something closer to bacteria or archaea than to anything with a face. This is also why so much of modern astrobiology research happens not by staring into deep space, but by digging into some of the most hostile environments Earth has to offer. Researchers study organisms called extremophils, life forms that have adapted to conditions once assumed to be completely incompatible with biology, because these creatures give us the closest real-world analog we have for what alien life might actually be built like. Tardigrades, sometimes called water bears, are perhaps the most famous example. These microscopic invertebrates are the only animals ever directly observed surviving the vacuum and radiation of open space, entering a dried-out, metabolically suspended state that lets them shrug off conditions that would instantly kill nearly every other multicellular organism on the planet. Halophiles are another compelling model, microbes that thrive in extremely salty environments and have been found surviving for tens of thousands of years, trapped inside tiny pockets of liquid within salt crystals, enduring extreme dryness, intense radiation, and severe chemical stress the entire time. Scientists studying these organisms under simulated planetary conditions aren't doing it out of pure curiosity. They're building a practical, testable reference library for what future space missions should actually be looking for, moving astrobiology away from speculation and toward something with real predictive teeth. And that reference library keeps pointing toward the same conclusion again and again. Life on another world may not look like a thriving, visible ecosystem at all. It might instead show up as something far more subtle, a trace gas in an atmosphere, an unusual mineral pattern in a rock, a molecular fragment buried in ancient sediment. That's a genuinely humbling realization if you grew up expecting first contact to look like a spaceship landing on the White House lawn. The actual first contact humanity is most likely to experience, if we're lucky enough to experience one at all, might be a spectroscopic anomaly buried in a stack of telescope data that a small team of scientists spends years arguing about before cautiously agreeing it probably, maybe, indicates something alive. Now, assuming microbial life really is out there and we eventually confirm it, the next natural question is what kind of environments it could be hiding in. And the honest answer is that the range of possibilities is much wider than most people assume. Physics and chemistry set hard boundaries on what biology can do anywhere in the universe, but within those boundaries, the variety of viable habitats is enormous. Gravity is one of the biggest variables. On a low-gravity world, structures that would collapse under their own weight on Earth become perfectly stable, which means organisms could plausibly grow taller, more delicate, and more extended without needing the kind of thick, dense support structures we rely on here. Wings, membranes, or fin-like extensions become far more practical tools for moving through a thin atmosphere, potentially producing life forms that glide or hover rather than walk or crawl. Flip that around to a high-gravity world and you'd expect the opposite pressures. Squat, dense, heavily reinforced body plans built to resist being crushed by their own mass, closer to the profile of something that hugs the ground than something that reaches for the sky. Atmosphere composition and thickness reshape biology just as dramatically. In a dense, murky, or dimly lit atmosphere, vision becomes a much less useful sense than it is on Earth, where sunlight is abundant and air is relatively clear. Organisms adapted to that kind of environment might rely far more heavily on chemical sensing, vibration detection, or highly sensitive forms of hearing instead of eyesight, developing broad respiratory surfaces or elaborate antenna-like structures to read their surroundings in ways we'd find completely alien, in the most literal sense of the word. High radiation environments, whether from a young, active star or a planet with a thin or absent magnetic field, would likely push evolution toward protection rather than exposure. thick shells, protective pigments, robust repair mechanisms at the cellular level, or an outright retreat underground into burrows and subsurface networks where radiation simply can't reach. None of this is unconstrained fantasy. Every one of these adaptations mirrors something biology has already produced right here on Earth, in extremophile bacteria, in deep-sea creatures that have never seen sunlight, in desert organisms that manage water loss with brutal efficiency. The aliens we're describing aren't wildly implausible science fiction creatures. They're extrapolations of solutions evolution has already proven, just tuned to different physical conditions. This is precisely why the search for alien life has increasingly shifted away from a narrow hunt for Earth clones and toward a much broader, more careful framework for interpreting ambiguous evidence, because the two biggest risks in this entire field turn out to be mirror images of each other. The first risk is the false positive, a signal that looks like it was produced by life, but actually has a purely chemical or geological explanation. The Venus phosphine story is the textbook example, and the K2-18b dimethyl sulfide debate may end up being another one, depending on how the ongoing reanalysis eventually settles. The second risk, and the one researchers increasingly say may be even more dangerous to the field's long-term credibility, is the false negative. Cases where life genuinely exists, or once existed, on a planet or moon, but our instruments simply fail to detect it, either because we're not looking for the right signature, because the evidence didn't preserve well, or because our detection thresholds aren't sensitive enough to catch it. A team of astrobiologists made exactly this argument in a 2026 paper, warning that current detection methods risk missing extraterrestrial life that's actually there, due to a combination of preservation problems, instrument limitations, and search strategies that are too narrowly targeted at Earth-like biosignatures. Their concern wasn't abstract. It was pointed directly at how billions of dollars in mission design and telescope time gets allocated, arguing that some current missions might genuinely need to be designed differently if we want any real chance of catching a false negative before it becomes a permanently missed opportunity. That concern has pushed some researchers toward a fundamentally different strategy for searching, one that doesn't rely on picking a single target gas and hoping it shows up. In 2026, a team introduced what they called an agnostic biosignature approach, built around modeling patterns like panspermia and terraforming across groups of planets rather than hunting for one specific molecular fingerprint on a single world. The core idea is elegant. Instead of asking, does this one planet have gas X? You ask whether a statistically meaningful pattern shows up across many planets at once, a pattern that would be very difficult to explain through non-biological processes acting independently and repeatedly across different worlds. This kind of approach exists specifically because individual biosignature gases, methane, oxygen, dimethyl sulfide, all of them can in principle be produced by non-living geological or photochemical processes under the right conditions, which means any single detection is always going to carry some irreducible uncertainty. Looking for patterns across populations of planets is one attempt to get around that fundamental ambiguity, and it represents a genuine shift in how the field thinks about evidence, moving away from a single smoking gun and towards something closer to an epidemiological signal, a trend that only life plausibly explains. It's also worth being honest about the noise surrounding this topic, because if you spend any time researching K2-18b or alien life more broadly, you will run into confident-sounding claims that go far beyond what the actual science supports. In the months following the 2025 dimethyl sulfide announcement, a number of online posts and articles claimed that NASA had definitively confirmed alien biology at overwhelming statistical confidence, some going so far as to tie the finding into completely unrelated conspiracy narratives involving classified government programs. None of that reflects the actual state of the published, peer-reviewed research. The real scientific record shows a contested 3 sigma at best signal that multiple independent reanalyses have since called into serious question, with some finding no statistically significant detection at all once the full data set is properly combined. That gap between the measured, cautious language of the actual papers and the confident, sensationalized language of secondary coverage is one of the most persistent problems in how this entire field gets communicated to the public, and it's worth keeping in mind every single time a new "We Found Aliens" headline crosses your feed. So where does all of this leave the search going forward? Webb was never actually built to be a dedicated biosignature hunter. It's an extraordinarily powerful general-purpose infrared telescope that happens to be sensitive enough to catch tantalizing hints like the K2-18b signal. But its instruments weren't designed from the ground up for the specific, demanding task of confirming life on a distant world. The first telescope purpose-built for that exact job is the Habitable Worlds Observatory, a NASA mission currently planned for launch sometime in the 2040s. Which will be capable of directly imaging exoplanets and capturing much higher resolution spectra than anything available today. That instrument is expected to be the one that finally has a real shot at resolving lingering questions like the one hanging over K2-18b with genuine clarity, rather than the current situation of competing 3 sigma claims and dueling reanalyses. In the meantime, researchers are also exploring entirely different avenues that don't depend on telescopes at all, including semi-autonomous robotic explorers capable of moving from rock to rock on a planetary surface and analyzing samples without waiting for slow, delayed instructions relayed across millions of miles from Earth. Technology aimed squarely at future missions to places like Mars and the icy moons of Jupiter and Saturn, where subsurface oceans could realistically be hiding exactly the kind of extremophile-style life this entire field has been modeling for decades. Step back from the individual claims and counterclaims for a moment, and a much bigger, quieter story starts to come into focus. We are living through the first period in human history where the search for alien life is a rigorous, well-funded, methodologically serious scientific discipline, rather than pure speculation confined to fiction. And that's a genuinely remarkable thing, even before a single confirmed detection ever arrives. The very fact that we can meaningfully debate whether a 3 sigma dimethyl sulfide signal on a planet 124 light-years away meets the bar for a real biosignature, using the same statistical rigor physicists apply to subatomic particle discoveries, tells you how far this field has matured. A generation ago, this entire conversation would have been almost entirely philosophical. Today, it's built on actual transmitted starlight, split into a spectrum, measured molecule by molecule, argued over in peer review, and reanalyzed by independent teams racing to be the most careful, not the most sensational. And when we do eventually get a real answer, whether it's a confirmed biosignature on a distant sub-Neptune, a microbial discovery in the subsurface ocean of Europa, or evidence buried in ancient Martian sediment, the shape of that discovery is very unlikely to match the picture most of us grew up with. There probably won't be a moment of a ship descending from the sky or a face-to-face encounter with something that speaks. What we're actually building toward, patiently and carefully, is the moment scientists agree, with high enough statistical confidence to satisfy the harshest peer reviewers on the planet, that a particular gas, a particular pattern, or a particular molecular fragment simply cannot be explained without life being involved somewhere in the process that produced it. That moment, whenever it finally comes, will be quieter than fiction ever imagined, and immeasurably more significant, because it will be real, it will be defensible, and it will be the first time in the entire history of our species that we can say, with actual evidence behind us, that we are not alone. What makes this moment in the search genuinely different from every prior era is the sheer density of data now being generated. Every transit of K2-18b that Webb captures adds another layer to a spectrum that gets picked apart by multiple independent research groups, each running their own atmospheric retrieval models across hundreds of possible molecular combinations. One recent systematic search conducted a wide-ranging scan across more than 600 candidate molecules, trying to find viable alternative explanations for the same spectral features originally attributed to dimethyl sulfide, precisely because ruling out mundane explanations is just as important scientifically as finding exotic ones. That's the level of rigor now baked into this field, and it's part of why claims that seemed exciting in early press coverage keep getting walked back, refined, or outright overturned once the full analytical machinery of the scientific community gets applied to them. It isn't that scientists are trying to dampen enthusiasm for the sake of it. It's that the actual stakes of confirming life beyond Earth are so enormous that the burden of proof has to be correspondingly enormous too, and every serious researcher in this space understands that getting it wrong even once could set public trust in the entire field back by years. There's also a deeper, more philosophical dimension to why alien life is expected to look so different from our fictional expectations, and it comes down to how narrow our own frame of reference actually is. Humans evolved on one planet, under one set of gravitational, atmospheric, and chemical conditions, shaped by one particular star's radiation output and one particular set of available elements. Every intuition we have about what a living thing should look like, how it should move, sense its environment, or organize itself, comes from that single, extremely specific dataset. When scientists model alternative biochemistries, exploring questions like whether life could be built around silicon instead of carbon, or whether liquid ammonia or methane could substitute for water as a solvent in sufficiently cold environments, they're deliberately trying to break free of that narrow frame. Carbon remains the leading candidate across nearly every serious model, mostly because of its unmatched ability to form stable, complex chains of molecules under a huge range of temperatures and pressures. But the fact that researchers take these alternative frameworks seriously at all tells you how open-minded the field has had to become. The universe doesn't owe us a version of life that fits comfortably inside human imagination, and the scientists doing this work know that better than anyone. None of this diminishes how extraordinary a confirmed detection would be. If anything, it raises the stakes because a genuinely confirmed biosignature, arrived at through the kind of exhaustive, adversarial, multi-team scrutiny that K2-18b has already been through and will likely continue to go through for years, would represent one of the most tested, most rigorously defended scientific claims in human history. It wouldn't be a single lucky observation. It would be the survivor of round after round of attempted debunking, the one signal that every skeptical reanalysis failed to explain away. That's a much higher bar than most people realize, and it's exactly why the field moves as cautiously as it does. Every false alarm, from Venusian phosphine to the shifting confidence levels around K2-18b's dimethyl sulfide, actually strengthens the eventual real discovery, because it forces the community to build ever more rigorous standards for what counts as real evidence before anyone is allowed to say the words, "we found it," out loud. So the honest, current answer to what alien life really might look like isn't a single image you can put on a poster. It's a layered, evolving picture built from real data, probably microbial rather than intelligent, probably hidden in subtle chemical traces rather than visible on a camera, probably shaped by extreme conditions in ways that mirror Earth's own extremophils, rather than inventing something biology has never tried before, and almost certainly announced to the world not through a single dramatic reveal, but through years of careful, contested, statistically grounded argument among scientists who understand exactly how much is riding on getting it right. That's not a disappointing story. It's a far more honest one, and honestly, once you understand how the process actually works, it's a lot more compelling than anything a movie script could invent, because every piece of it is real. It's happening right now, in active telescopes and active labs, and the next chapter of it is still being written. There's another side to this search that rarely gets the same attention as biosignature gases, and that's the hunt for what scientists call technosignatures, evidence not of simple biology, but of engineering, something built rather than merely grown. This is the domain most people actually picture when they hear the word aliens: radio broadcasts, structures, deliberate signals sent across the galaxy by a mind capable of intention. The search for those signals has been running in one form or another for decades, and it operates on a completely different set of assumptions than the biosignature hunt happening around planets like K2-18b. Where biosignature science looks for the accidental chemical byproducts of life simply existing, technosignature science looks for evidence of purpose, and that distinction changes everything about how researchers think about detectability. A civilization broadcasting a constant, easily recognizable signal on a familiar frequency is the version most searches have historically been built to catch, but there's a compelling argument that this assumption might be almost backwards. If an advanced civilization operates on timescales vastly different from our own, a signal meant to be obvious to them could be functionally invisible to us, not because it's weak, but because it's timed or structured in a way we simply aren't built to notice.